So today we're going to talk about classifying matter. Okay, so before we begin, I want to review just a few of the things from the last video. Democritus and Aristotle. Democritus thought that stuff was made out of atoms and that they're little mini versions of the whole. And Aristotle thought that stuff was made of combinations of 5 elements: earth, water, air, fire, and something called ether. Now, both of these philosophers from 2,000 years ago were sort of right, but also sort of wrong. Okay, today's modern understanding of what stuff is made out of has pieces of both of these in them. For example, we do believe that things is made out of elements, like Aristotle did, combinations of these elements, which is what I'm going to talk about today. But it's not those 5 elements. In fact, earth, water, air, fire, and ether are no longer considered elements at all, but other things. Now, Democritus thought stuff was made out of atoms, but he thought there were an infinite number of atoms and every material was made of its own version of those atoms. That's not entirely wrong, but you can have some atoms combined together to make new atoms, and when you get down to the smallest atoms that can kind of be broken apart, that's what we call an element. So basically our modern understanding now is both of these ideas with some of the stuff kind of taken out there. The 5 elements gone, but the idea of elements is still there. The infinite number of atoms, many versions of the whole thing, that's gone, but things are made out of discrete bits called atoms. Okay? Now, alchemists in the Middle Ages started to discover this idea that both of them might be right. Things are made out of atoms, but also there's specific atoms that combine to make other things. And so as they were discovering things about new materials, they started trying to figure out what these elements were. You can still see on this chart, this is an alchemist chart of elements, that they have fire, water, air, and earth still. They also have a few things like Mercury and Venus and Mars. The idea of ether kind of developed into different elements for the different planets. But they are starting to discover certain things that are actually elements. For example, copper and lead and arsenic and phosphorus. There are a few things that aren't actually elements, like salt and vinegar. Those aren't actually elements, but we were kind of headed in the right track here.
Most chemists believed fire was due to some fiery principle that was given up during combustion. And all our senses seem to confirm this idea. Heat, light, smoke, all are released as the fire burns. By the mid-1700s, this essence of fire had been given a name: phlogiston. Phlogiston was the foundation of chemistry's leading theory for nearly a century because it seemed to explain things like metals and rust. When iron ore was heated in the presence of charcoal, phlogiston from the charcoal fused with the ore to form metallic iron. When the iron was exposed to air or water, the metal released its phlogiston as it rusted. Other metals went through the same process, forming the green verdigris of copper, for example. Ore plus phlogiston equals metal. Metal minus phlogiston equals rust, or what was then called a calx.
Only there was a problem. The calx was heavier than the metal, even though phlogiston had left the metal. It's lost something, and yet it was heavier.
The calx should weigh less than the original metal, but it doesn't. The calx is heavier than the metal.
Though many chemists were aware of this contradiction, they let it pass because phlogiston otherwise worked so well. But Lavoisier was really troubled by this because he was obsessed with the weights of his experimental ingredients.
Lavoisier was very careful to get very good instruments. He probably at one point had the largest and most complete private laboratory on Earth.
With my precision scales, imported from England at great expense, I measure the weight of each substance at the beginning and end of every chemical reaction.
Lavoisier was a master of this balance sheet kind of chemistry. Remember, he was a tax administrator by day. He knew a lot about accounting, and so this kind of ledger keeping was natural to him.
It is a fundamental truth of chemistry that the same amount of matter exists before and after each experiment. Nothing new is created, nothing lost. The whole art of performing chemical experiments rests on this principle.
Today we call this idea the conservation of matter.
When you carry out a chemical reaction, what comes out has to be exactly equal to what goes in.
The total weight must remain precisely the same. If not, there's an error somewhere.
He wasn't the first to assume conservation of matter, but Lavoisier applied this idea more rigorously than anyone had before. And it worked very effectively as a tool of discovery.
The power of Lavoisier's method would become clear in October 1772, when he set out to solve the riddle of why metals gain weight when they form calxes.
Common sense suggested that when things rust, they must lose weight. They fall apart, they become brittle and weak. Lavoisier was interested in actually measuring what happened.
He conducted his experiments in public, relying on a huge burning lens that focused the sun's rays to produce intense heat, while elegantly dressed bystanders watched in amazement. Lavoisier placed a calx of lead mixed with charcoal inside a glass vessel partially filled with water, then subjected it to the intense heat of the burning lens. The result was extraordinary.
As the calx changes back into the metal, it releases a large quantity of air. This air forms a volume 1,000 times greater than the calx it came from.
This startling finding suggested a radical idea. If air came out as the calx changed back into a metal, could it have gone in when the calx was formed? Could air be the reason calxes were heavier than expected? Lavoisier also found that when he burned elements like sulfur, they too gained weight.
There was then no doubt. I realized that the increase in weight occurs because a portion of the air is absorbed into the solid material.
He knew he was onto something very important. He knew that the element did not lose mass, it gained mass. It took up some part of the air.
So Antoine Lavoisier, he is an alchemist who is considered the father of modern chemistry. He's the point where we went from alchemy to chemistry. The reason why is because he insisted on very, very careful measurements and evidence to support his ideas. Okay, now he is responsible for a whole bunch of things, but some of the most important ones is that he came up with what's called the law of conservation of mass. He helped construct the metric system, which we've been using over the last couple of weeks, and which is now used around the world. He also disproved the alchemist idea of phlogiston, which was an element they believed existed, in favor of something in the air, which he named oxygen. Okay. Studying the oxygen was actually discovered by Joseph Priestley. He was actually able to disprove Aristotle's 5 elements. So it's Antoine Lavoisier where we've kind of went from alchemy to modern chemistry, disproving those 5 elements that Aristotle came up with, that they don't actually exist, but there are elements that do exist. They're just different ones. Okay? So Antoine Lavoisier, huge important scientist for changing chemistry from alchemy here. Discovered a lot of important things. So the conservation of mass that he came up with, this idea is that stuff remains stuff. So if I were to take a match and I were to burn it, it would turn into ash and carbon dioxide and other things. But if I am able to collect all of the material it turned into, including the smoke and the carbon dioxide and the things that float off into the air, and seal it in that container, it would actually weigh exactly the same before as after. Nothing would change in terms of the mass. Stuff remains stuff, and we don't lose any. We don't destroy any. Okay? So the law of conservation of mass is that mass cannot be created. It cannot be destroyed during a change. It can only be rearranged. So the match turns into smoke and carbon dioxide, but the smoke and carbon dioxide still weigh the same as the match did that it came from. So, way we think of this now, let's say we were going to make a product called hydrogen chloride gas. It's It's made out of hydrogen and chlorine. If I took 2 grams of hydrogen and 70.9 grams of chlorine and I combine them and I make this new product, they merge together and they become a new particle, a new substance, but that new substance would weigh the same as the materials that make it up. So it would weigh 72.9, the two things that made it up added together. So let me give you guys an example of how a problem like this would work. Methane, CH4, it burns with oxygen, that's O2, and produces carbon dioxide and H2O, water. If 32.0 grams of methane are burned, it will require 72.0 grams of oxygen. So what will be the mass of the carbon dioxide in the water that's produced? So what will be the mass of the products afterwards, if this is the mass of the things it took to create it? Well, it's just simple addition, okay? 32 grams plus 72.0 grams equals 104.0 grams. And since both those have 1 decimal, my answer also has 1 decimal. Another example, sodium chloride. It's formed by the reaction of sodium and chlorine gas. Now, if 45.98 grams of sodium combines with some chlorine gas, but since it's a gas, I didn't measure it, okay, but it forms 116.89 grams of sodium chloride, what was the mass of that chlorine gas that was used in this reaction? Well, we know that all of that extra mass for the sodium chloride there to form that 116.89 grams, all of the extra came from the chlorine. 45.98 of it came from the sodium. So if we just do some simple subtraction here, 116.89 grams, that's the sodium and the chlorine compound together, subtract the sodium part, 45.98 grams, you get 70.91 grams. So it took 70.91 grams of chlorine in this reaction here. That's how much chlorine was actually used. Conservation of mass. It had to come from somewhere. Now, when we talk about changing things, there are 2 types of changes. There's physical changes and there's chemical changes. A physical change is a change which does not alter the composition. So it's going to be the same substance that it was before the change. There's going to be no chemical bonds broken, no new chemical bonds are going to be formed. A couple of examples of a physical change: tearing, crushing, bending. Okay? Anything in which you alter it but do not change what it is, that is a physical change. This also includes phase changes, like if you freeze something or if you melt it. It's still the same thing afterwards, but it's different in a way. All right? Now, this is what a lot of manufacturing processes deal with. I mean, they take a sheet of metal, they cut it into pieces, they form it into other things, but it's still the same material you started with. So it's all physical changes. Chemical changes, on the other hand, chemical changes, this is when you actually get a new material. It's a change in composition. So when new substance is created out of the original substances, chemical bonds are either being broken or new chemical bonds are being formed. Examples of this: combustion, where you burn something and it turns into carbon dioxide, water, smoke, a few other things, new materials. Rusting, iron and oxygen are turning into iron oxide, which is this red material. Corrosion, tarnishing, formation of a precipitate. When you get something that was a liquid that kind of suddenly forms a solid there, that's what a precipitate is, that would be a chemical change, okay, as it creates that new solid from a couple of liquids. So any chemical change, new material.
Pan Balance is a veteran monitor of change. Flame and smoke carry away substance from the charred matchsticks. The lightened pan rises. In some changes, weight is gained. The white powder is a drying agent that picks up water from the air to become a little heavier. The sensitive balance did not ignore it. The famous Alka-Seltzer fizz departs invisibly. The bubbles escape. the sample becomes lighter. One modification only. Tighten the cap to keep the bubbles in. Now nothing can escape or enter, and the weight does not change. We are on the track of an unchanging quantity. Okay, seal her up.
Let's put the top on it. We may not have totally perfected the electrically lit candle, but we're working on it real hard.
Okay, Tom, let's put them on. It'll take more. We balance the box on an antique farm scale. Now for the fine weights. Okay, try some of those off. Getting close, anyway. Yeah. Let me deliberately put some here to see how well we're doing. I'm putting 2 coins. I'd say we balance it to about 1/4. When I figure that out, that's better than a part in 1,000 for the whole weight. Okay, we have a good seal, we have a balance. Let's start it up. We want to move away the stools, and I'll turn the master switch. I will trigger by moving magnet A so that ball B can fall upon mousetrap C, I hope. But for the rest, you must watch for yourself. Aha! A glow, motion, a candle, pop, sparklers. Oh, that's beautiful. The wind-coupled fan. Popcorn. The barrage begins. Plenty of change. Firecrackers. And still it glows. The cube of smoke is good evidence that this box is pretty tightly sealed. The balance is well retained. All the changes we saw, from the steam-expanded popcorn to the discharging storage battery, to the fan that drives the pinwheel, to the motions of the little toys and the expansion of the springs, to the explosion of the firecrackers and the glow of the sparkler, all those chemical reactions, nothing changed in the balance. Weight, that which we measure on the balance, remains constant during many changes. That's what we've shown here in a rowdy version of an elegant experiment that's been done repeatedly with great care ever since the 18th century and remains a pillar of science today.